I'm Stacy, and welcome to my talk on totally p-adic numbers of degree 3. First, I want to acknowledge that my home sits on land within the territory of the Piscataway people, who are the original stewards of this land. I live in Chestertown, Maryland, on the eastern shore of Maryland in the United States. Now, today in this talk, we're going to try to get really an introduction into my topic. So we're going to go through some history, height functions, Lamar's conjecture, what's a totally real number, develop the motivation for the work that I've done, and then I'll tell you some of my results. For more details, please see my paper or come to my talk next Wednesday. So first, the logarithmic Bay height. The height of a rational number in reduced form is the log of the max of the absolute value of the numerator and the denominator. So the height of an algebraic number really gives a measure of the arithmetic complexity of the number, and not necessarily the size of the number in the traditional sense of absolute value. For example, the height of 1/3 is log 3, which is just over 1, whereas the height of 10,001 over 30,000 is just over 10, even though those numbers are really close together on the number line. We can extend this height function from rational numbers to all algebraic numbers by the following equation, where d is the degree of the minimal polynomial of the algebraic number, a is the leading coefficient of the minimal polynomial, and the alpha sub j's are the roots of the minimal polynomial. And log plus is either 0 or the log, whichever is bigger. Now, some properties of the height function. If two numbers share a minimal polynomial, then they're going to have the same height. And that's because in that previous slide, you see those two minimal polynomials, they're going to have the same leading coefficient, they're going to have the same degree, and the collection of all the roots are going to be the same. Additionally, for any integer n, the height of alpha to the n is the absolute value of n times the height of alpha, so that n can pop out using properties of logarithms. The height is non-negative, and it's equal to 0 if and only if alpha is either 0 or a root of unity. So we're interested in the height, small height, of numbers whose height is non-zero. The Northcott property tells us that there's finitely many algebraic numbers of bounded height and degree. What I mean by that is if you have a bound on height, b, and a bound on degree, d, there's only finitely many numbers whose height is less than b and whose minimal polynomial has degree less than d. This property was used by Cantor in 1874 to prove that the algebraic numbers are countable. Additionally, we have what's called the height length bound. The length of a polynomial is the sum of the absolute value of the coefficients. D here is the degree of the polynomial, and h of alpha is the height of alpha. So if we want to find all polynomials that are bounded of a particular degree, that are bounded by a particular height, we can use this height length bound to search all polynomials of bounded length. By property b, the dth root of 2 has height 1 over d log 2. Because of this, we can think about letting d go off to infinity, which is going to create smaller and smaller and smaller numbers, or numbers of smaller and smaller and smaller height. So they can become arbitrarily small. So if we're looking for what's the smallest height number, we can really create a number smaller than any bound that you can find. So in 1933, Lamar created a conjecture. He posed the question, does there exist some positive epsilon such that the height of alpha is greater than or equal to epsilon over d, where d is the degree of the number alpha? He was able to find by hand this 10th degree polynomial. We've plotted the roots here on the complex plane, and we've also, the orange dots are the unit circle. So we can see that 8 of the dots, the roots are actually on the unit circle, and then we have one pair that pops out, one to the right and one to the left of 1. And the height of a root of this polynomial is about 0.016. Now, Lamar's conjecture is currently open. Nobody has either found a better polynomial, nor has anyone been able to prove that that is the best. The current record was proved in 1979 by Dobrowski, who was able to find that the height of alpha is bounded below by 1 over d log of this mess. Now, this doesn't quite satisfy the Lamar's conjecture because of that log d over log d. That d buried in there would need to just be constants in order for it to satisfy Lamar's conjecture. But for certain subsets of algebraic numbers, there are solutions to Lamar's conjecture. So, let's say a number is totally real. What I mean by totally real is that its minimal polynomial splits completely over R. For example, the square root of 2 is totally real since it has minimal polynomial x squared minus 2 with roots positive and negative 2, both of which are on the real line. However, the cube root of 2 is not totally real because the minimal polynomial is x cubed minus 2, which has two non-real roots. It has the cube root of 2 and it's got that complex conjugate pair that pops out off the x-axis. In 1973, Schinzel proved that if alpha is a totally real algebraic number, not equal to 0, 1, or negative 1, then the height of alpha is bounded below by 1/2 log 1 plus root 5 over 2. And there's even equality. So when Schinzel proved this, he used a systems of inequalities, and for there to be a case of equality in that, all of those inequalities have to be equal at the exact same time. And the number 1 plus root 5 over 2 does in fact achieve this bound. So, my work is in totally p-adic numbers, which is analogous to totally real. Only we're going to look over QP, which is the field of p-adic numbers. So for that, we're going to look at the p-adic absolute value, which measures the divisibility of a prime p in the denominator of a number. So if you have a number, a rational number, with more and more and more primes, p's, powers of your prime p in the denominator, that number is going to be bigger p-adically. If we complete the rational numbers under this absolute value, we attain the field QP. We're going to say that a number is totally p-adic if its minimal polynomial splits completely over QP. Now, we're going to create a doubly indexed set, tau sub dp, where d is the degree and p is the prime, and tau sub dp is the smallest non-zero height of a degree d number that splits completely over the prime p. For example, along the top we have degree and along the side we have primes. So if I just look at the column under 2, I'm just looking at quadratic numbers. I'm just looking at roots of degree 2 polynomials. If I'm looking at a row, then I'm just looking at, for example, the row under 5. I'm looking at all of the different heights that split completely over Q5 of various degrees. When I began doing this work, I was actually looking at the row 3. I was looking at Q3, and I got very frustrated, and I switched to looking at a column. So I started with 2 because I do know the quadratic formula, and I know a lot about how quadratic polynomials split. So the first question that I answered was, given a prime p, can we determine tau sub 2p? And the answer is yes. You can give me any prime, and I can tell you tau sub 2p, simply by taking your prime, modding out by 5, looking at that residue class, and that's going to give me the answer. For example, if you give me a prime, and I mod out by 5, and I attain either 1 or 4, then tau sub 2p is going to be 1/2 log 1 plus root 5 over 2. Otherwise, tau sub 2p will be 1/2 log 2. And this theorem is proven, the main tools are really quadratic formula and quadratic reciprocity. We're really looking at when the discriminant of a quadratic equation splits. All right, to begin this proof, we're going to look at all quadratic polynomials whose roots have height 1/2 log 1 plus root 5 over 2. And that's actually only attained by the roots of x squared plus or minus x minus 1. So it's just those two polynomials. All other quadratic polynomials will have roots whose height is larger than that. The next largest height attained is 1/2 log 2. So here I have listed 3 examples of polynomials whose roots have 1/2 log 2. And I've also included here the discriminant, because the discriminant is going to tell us the splitting behavior, right? If I use the quadratic formula, I've got the square root of b squared minus 4ac. I need to know when that square root exists within my field. So if we were looking at when these polynomials split over R, I would be looking at whether the square root of those numbers are real. So in that case, 5 and 2 would satisfy, and -2 and -1 would not. Now, if we're looking at QP, it gets a little different. So the polynomials x squared plus or minus x minus 1 split over QP if and only if 5 is a square modulo p. By quadratic reciprocity, 5 is a square mod p exactly when p is a square mod 5. And that happens when p is congruent to 1 or 4 mod 5. And that, here we're talking about the Legendre symbol, the parentheses. Also, 5 is not a square in Q5, so I know that x squared plus or minus x minus 1 do not split over Q5. By properties of the Legendre symbol, I know that I can multiply the symbol of -1 over p times 2 over p, and I can multiply the numerator. So I'll get -2 over p. Now for all odd primes, these values of the symbols must be positive or -1. Because of that, at least one of these numbers has to be +1. You can't have -1 times -1 equals -1. Whichever of those symbols has the value 1 for your prime, the associated polynomial must split over QP. Since x squared plus and minus x minus 1 do not split over Z2, they do not split over Q2. And by Hensel's lemma, x squared plus x plus 2 does split over Q2. So we have that tau sub 2 equals 1/2 log 2. So having solved the quadratic case, right, we have reduced this to the point where you can bring a prime to me, I can look at your prime, I can really just look at the last digit of it, I can mod out by 5, and I can tell you immediately the answer to your question of what's the smallest height of a degree 2 number that splits completely over your prime. Which brings us to the next question of, can we do it in degree 3? Well, we don't have the quadratic formula anymore, but we have a version of it. We have Cardano's method, which is a way of looking at a cubic polynomial and determining what the roots are. We use some Galois theory, and we rely very heavily on sage math. Now first let's start with Cardano's method and look at what that really is. And it's analogous to completing the square as opposed to the quadratic formula. And we need to use this version because when we take square roots and cube roots in QP, we need to be very, very careful. In R, we know that every number has exactly 1 cube root in R, and that's not the case for QP. So with Cardano's method, we start with a polynomial of the form x cubed plus ax plus b. Now, any cubic polynomial can be rewritten in this form through depression, change of variables. And what that is going to do is it's going to shift the roots, but it's going to shift them using field operations. And so If the roots of the original polynomial fall into QP, the roots of the depressed polynomial will also fall into QP. So we're going to be using the form x cubed plus ax plus b. We're going to let zeta be a primitive cube root of unity. We're going to suppose a is non-zero. And then we're going to let u cubed be negative b plus the square root of b squared plus 4a cubed over 27 all over 2. And then we'll define v to be negative a over 3u. Then the roots of f can be written as u plus v, zeta u plus zeta squared v, and zeta squared u plus zeta v. Which raises the question, when are these three roots going to be in QP? And that really is going to depend on whether P is congruent to 1 or 2 mod 3. Because if P is congruent to 1 mod 3, F is going to split over QP if and only if U is an element of QP. If we can show that U is in QP, our polynomial splits. If our prime is congruent to 2 mod 3, we need to prove that U is not in QP in order for it to split. Thank you for watching, and for more details, please see my paper or come to my talk on Wednesday.